Alright, so I wanted to make a little video just to recap the things that we did or were about to do in Lecture 8 before the camera died. So here's the high points. We talked about homomorphisms for a little bit. I reminded you guys the definition of homomorphism is just a structure-preserving map between two groups. And I mentioned that we have previously noticed that, you know, the nth power of a group element transforms to the nth power of the image, like this. We proved it for isomorphism, but I mentioned when we did that proof works just as well for homomorphism. And we also have this theorem from our previous work. The identity maps to the identity. The inverse of the image of the inverse is the inverse of the image, and the nth power maps to the nth power in that sense. In the additive notation, if each and h were additive, we'd map 0 to 0. We, in some sense, could pull minuses out of such a thing. In other words, it maps the negative to the negative. And repeated addition maps to repeated addition. Alright, so we have those things. Then, I mentioned proposition 2.8.12. Now, proposition 2.8.12, and by the way, I'm going to make a separate video with lecture 9, so this video would just cover the fun items in lecture 8. It shouldn't take too long, actually. So in words, proposition 2.8.12 says that the image and inverse image of a subgroup under a homomorphism is once more a subgroup. And I'll prove this in the next couple minutes. I then defined kernel and image of a homomorphism, and I gave a couple of examples. I'll do that again here. All right, let's get to it then. So the first part of proposition 2.8.12 is, come on, you can do it. Stop that. Stupid. There we go. Sorry, got that out of my system. Is that if we have a homomorphism, group homomorphism phi, from group G1 to group G2, and we have a subgroup U1 of G1, then the image of U1 under phi is a subgroup of G2. So here's the proof. First of all, of course, I'll suppose it's got a homomorphism. I'll suppose that the image is defined as it usually is, set of outputs with the input from U1. I'm also going to suppose that U1 is a subgroup of G1. All right. Then I'm going to let E1 and E2 be the identities of G1 and G2 respective. Notice that since U1 is a subgroup of G1, it means that E1 is in the subgroup, and by our property of homomorphisms, phi of E1 is E2, but that says that E2 is actually an element of the image of phi of U1. Since E1 is an element of U1 and it maps to E2, that means E2 is in the image, which then says that the image is non-empty, and we should also notice, essentially from the definition, that the image is a subset of G2. So this means we can apply one of our subgroup tests, you know, either the one-step or two-step. Let's see what I do. So pick A and B in the image. That means that there exist x and y in U1 such that A maps A is equal to phi of x and B is equal to phi of y. But then, notice that x and y are in the subgroup, and since the subgroup is closed under multiplication and inversion, xy inverse is also in U1. Consequently, if we look at AB inverse, well, that's phi of x, phi of y inverse, but by the property of homomorphism, we can bring the inverse inside. And then by the definition of structure-preserving homomorphism, we can break the product of these images to the image of the product, like so. But then that implies that the A times B inverse is equal to phi of that. That is in U1, as we just argued, which means that AB inverse is in the image of U1 under phi, which is to say that A and B in the image implies AB inverse is in the image, thus the image under U1 of phi is a subgroup of G2 by the one-step subgroup test. So there you go. Next, come on. Eventually I'll learn how to, oh well. Fine. All right, next up here, the second part of proposition 2.8.12, about a homomorphism from G1 to G2, both groups, of course. U2 a subgroup of the codomain. Then the inverse image under phi of U2 is a subgroup of G1. I should emphasize here, guys, that this does not mean that phi inverse as a mapping exists. This is a set theoretic thing, and this is defined even for functions which are not one-to-one, okay? In particular, let's suppose we got a group homomorphism again, and U2 is a subgroup group of G2. We define the inverse image to be the set of points in the domain which map to U2 in the codomain. So x in G1 says that phi of x is an element of U2. That defines the inverse image of U2 under phi. And so, of course, by construction, the inverse image is a subset of G1. And again, looking at the identity maps to the identity, but that means that the identity E1 is an element of the inverse image under phi of U2 because E2 is in U2. Then, so that means that the inverse image is non-empty, right? And it's a subset. So a non-empty subset, we can apply the subgroup test. Let x and y be in the inverse image of U2. It implies that phi of x and phi of y are in U2. And so the product phi of x times phi of y is equal to phi of xy by the homomorphism structure preserving property. That's in U2 because U2 is closed under multiplication, which means that, x and y, uno momento. Let's see here. Oh, because I'm using that phi of x and phi of y are both in U2, which means that their product is in U2. But that also means that the image of x and y under phi is in U2, but that means that xy is in the inverse image of U2. And so likewise, if we think about x being in the inverse image of U2, that gives phi of x is in U2, right? But then phi of x inverse is in U2 because U2 is closed under inversion. But then by the property of the homomorphism, that means that phi of x inverse is in U2. But then that means that x inverse is itself in the inverse image of U2 under phi by definition of inverse image. So, in short, we have shown that if x and y are in the inverse image of U2, then both xy and x inverse are in the image of U2, and we can conclude by the two-step subgroup test that the inverse image under U2 of the inverse image of U2 under phi is a subgroup of G1, which is pretty cool. And, I mean, the most, of course, important application of this theorem comes to us in its application to the inverse, really the inverse image of the trivial group and also the forward image of the whole domain. The image of the whole domain is called the image. The kernel is the inverse image. If you sort through this, what this is sorry, I meant to write it on here. You can see that if you work through it, the kernel of phi is in fact equal to phi inverse of the identity of H. So that's the inverse image of the trivial subgroup of H. That's the so-called kernel of the map. And a corollary to the proposition I just proved, of course, would be that, well, the kernel is a subgroup of the domain, and the image is a subgroup of the codomain. And here's a couple of examples, actually 3 examples, 2 of which I already gave in class. So sorry, I'm in reruns for those of you who are there. First of all, the determinant map gives us a homomorphism from invertible matrices to non-zero real numbers under multiplication. Here's the determinant, product of determinant of the products. That gives us the homomorphism. And the kernel is just the set of matrices that have determinant 1, because 1 is the identity of the multiplicative group of non-zero real numbers. But of course, this is just SLNR, the special linear group of n by n real matrices. And so this, exhibiting this map and noting that it's the kernel, that proves that SLN is a subgroup of GLNR. It's pretty nice. The next example, sorry, I'll hear just a second. Whatever. In the next example, mapping from the reals to the non-zero complexes by the imaginary exponential, it satisfies this law of exponents. This is actually a sneaky way of compressing the adding angles formula for both sine and cosine. If you get into it, the proof of this is both adding angles formulas for sine and cosine combined. If you haven't never worked through that, you ought to. Anyway, so phi is a homomorphism from the additive group of the reals to the multiplicative group of non-zero complex numbers. And the image under phi is actually just e to the I theta. That's a set of unimodular, or length 1 complex numbers And you could also show that anything on the complex in the inner circle is on there. So it's not only it's a subset of that, yeah, sure, but it's also everything in there. The whole unit circle is the image of phi. So image of phi then is a subgroup of the non-zero complex numbers, and as such is a group. Example 3, which I failed to mention in class, but I will mention now, is the sine function, which assigns to every permutation in Sn either plus or minus 1, 1 for the even permutations, minus 1 for the odd permutations, based on the even or an odd number of transpositions it takes to form a given permutation, as we have discussed in prequel 3. That number, even or odd as it may be, is well, it's not unique, but it is unique up to a multiple of 2. So this is a well-defined map, and anyway, it's in fact a homomorphism. I consider all 4 cases in Lecture 8 in the explicit notes. More to the point here, the interesting thing is that the kernel of the sine function is the alternating group, the set of even permutations, which then is shown to be a subgroup of Sn. So pretty nice application of the kernel and image, I think, here. An important thing to know about, oftentimes one of the best ways to convince your instructor that you really understand what you're doing is to exhibit a subgroup, in fact, as the kernel of a map. It would take a truly I'd have to be a real jerk to say, oh, you don't know what you're doing when you say that, and you say it in a cogent way. But anyway, there's of course more than one way to show something's a subgroup, and now we just have 2 more ways in terms of image or subgroup. Of course, we still have first one-step and 2-step subgroup tests, or just the plain old check all the axioms for the group for that given subgroup and see that it works. I mean, these are all options. Anyway, that's it for now, and next I will move on to Lecture 9. Thanks, guys.